Okay. All right. So welcome everyone. My name is Babak Saraje at the Indiana University. So I'm the host and moderator today. I think a lot of you have seen one or more of our Colloquium series. If this is the first time you're here, we are part of the Virtual Science Forum, which is an open, collaborative, and volunteer-run initiative. And our aim is to facilitate online scientific seminars and conferences and events. If you would like to join us, we're open, we're an open group. All of our meetings are open, our documents are open, and I am posting some links where you can go and see our documents and maybe join us. All of our talks that are recorded are available on YouTube, and I would also like to thank institutional support that makes this possible, in particular, Kavli Institute of Nanoscience Health. So just a quick note on the Q&A. So you should find a button for raising your hand is usually located under the participant panel. And we welcome your questions during the talk as well. I will moderate the participant panel. When you raise your hand, I can see it, and I can unmute you and let you ask your question first. All right, so let's move to our colloquium today, which is given by Mohammad Hafezi of University of Maryland and Joint Quantum Institute. He's going to tell us about the recent work on quantum optics and correlated electrons. Mohammad?
Okay, thanks, Babak, for the introduction and also the invitation. So this is, I understand, it's a colloquium style, so I would like to keep it very broad. The idea is that, the idea is actually very simple. We would like to apply and explore quantum optical techniques to correlated electrons. So that's a very simple message, that this is quantum optics. We love it, you know, for example, cavity QED, all the interesting developments because of quantum information sciences that has been majorly focused on manipulation of single excitations, like a single quantum dot, diamond centers, etc., or excitons. Now, can we apply it to a correlated electron systems? Can we use these techniques to create and control many-body states of electrons? Okay. So this is a very broad topic, so I would like to put it into a little bit of perspective. So in quantum optics, we would like to think of the space of possibilities in the following. So on the x-axis, we have the photon number, how many photons we have in the system. Like we have a weak laser field or a strong laser field, etc. So this is the x-axis. The y-axis is the interaction strength per photon. So usually this is fixed. You know, if you think of like mediating interaction between photons, like nonlinear optics, photons very weakly interact with each other, and the reason that they interact is through mediation with matter. So you have some photons, they interact with matter, and then when the other photons come, they see the influence of the previous photons. That's why there will be some photon-photon interaction mediated by the atom. So in the nature, this is kind of fixed by Feynman-Strachan factor. So you would think that interaction strength per photon is fixed. What one can do is that we can put this material inside a cavity such that the photon stays there for a long time, and then effectively that photon-photon interaction increases. The reason I just chose a duck was that just Keynote had that, so I used it. The idea is that you can have this cavity, it can have any kind of modes. It can be a single mode, many modes, etc. You have like really full capability of forming what kind of resonant modes of photons we have in the system. So this is the y-axis, okay? So now on this corner, you have low photon number and low interaction. So that's kind of linear optics, like integrated optics, silicon photonics. If you go up, if you increase the interaction, then you have quantum photon-photon optics, like cavity QED, like circuit QED. If you now increase the number of photons, you go to this classical nonlinear optics, like solitons, etc. And then people are trying to move into this region where you have now many photons, and also they are strongly interacting with each other. Okay, so this is kind of the state of the quantum optics. Now, it turns out there is another axis to this two-dimensional space of possibilities, and that's the strength of electron-electron correlation. How strongly our matter, our electron matter, are interacting with each other. For example, in quantum dots, I can just, oh, there is a question. So should I answer questions? What's the rule of, I cannot hear you. Oh.
Yep, I will unmute.
Okay, well, I guess that you're starting to answer the question that I was going to pose. In other words, what I was going to say was, well, it seems to me that the question of whether you're in the regime of classical nonlinear optics or whether you're in the regime of quantum many-body physics is going to depend not just on how many photons you've got, but whether or not you're able to treat those photons in, say, a mean field way, as opposed to in a way where you have to really think about the details of the interactions. Now, that looks like where you're going on this third axis.
Yeah. So,
but,
yeah.
But you see what my issue is. It sounds like I could still have lots and lots of photons, just like in, in solids, I can have lots and lots of electrons, but unless they're correlated, it's not going to make it into a quantum many-body problem.
Indeed, and what
sounds like you're going there now, anyway.
Yeah. So as I said, photons do very weakly interact with each other. So almost don't interact with each other. So it has to be through the matter. And then usually what we have is that we don't consider that the matter itself is strongly interacting, or effectively it's a system that we can think of these quasi-particles as non-interacting entities. For example, excitons that are weakly interacting with each other. So the light-matter interaction will remain weak. Now, I would like to go in this direction, that I would like to now these material strongly interact with each other. For example, if I consider a Mott insulator, or if I consider a fractional quantum Hall state, how light-matter interaction would change and what kind of physics I can expect. So instead of doing this three-dimensional space of possibilities, I would now go back to two-dimension. It's easier to show it. So on this axis, I have the electronic correlation strength. And on this side, I have the interaction strength per photon. So then on this side, I have, they're weakly interacting with each other. So if I want to change anything seriously in the material, not perturbatively, not just probing the system, but change really the behavior of the system, I have to put many photons in the system. And that's these laser-driven systems. And examples of it, the recent example is, for example, Fluke topological insulator, that you have a linear system, it's a band theory, and then you drive it optically, and then you fundamentally change the underlying physics. Now, I can put the system inside a cavity and enhance this photon-photon interaction. And as I said, you can go to the regime of cavity QED, circuit QED, exciton polariton, optomechanics, etc. Now, the goal of this talk, and give like a survey, is to go in this direction. We would like to add, we would like to consider material with strong interaction. For example, fractional quantum Hall, Mott insulators, superconductors, etc. And then see how laser-driven, like putting many photons in the system, can change dramatically the behavior of the system. For example, can we have light-enhanced superconductivity, light-induced ferroelectricity, etc. And even more intriguing, can we have no light, just fluctuations of vacuum of photons mediate the strong interaction for these electrons, and maybe we can have cavity-induced superconductivity or fractional quantum Hall states in the cavity, etc. So these, I have to say, they're very controversial because they're dealing with real material. So it's not as simple as this side of the story. We have to not only take care of the interaction between photons, but also electrons. And I like to present it like this, that on this side, you have this microscopic theories that are cute and are very nice. And you have on this side this dirty experiments, and everyone is trying to get to this gold mine, but in fact it's something like this. So you're going to experiment in this direction and the microscopic theory in this direction. So one has to take these theories and proposals with a grain of salt, and they're not like one-to-one. There is no one-to-one correspondence. So with that in mind, and I missed because Bill asked the question, and we are actually writing a review, like a perspective on this topic. And my talk cannot be a survey of all the works that people are doing in this exciting field. This talk will be the works that we have been doing, some theoretical works. And the first part of the talk would be focused on light-induced topological states or optical control of topological states, like for example, quantum Hall states, and how we can use light to probe and manipulate quantum Hall states. And the second part of the talk has to do with now using light on superconductors. Can we use light to enhance superconductivity or induce it? Okay. So if that kind of motivation has not motivated you, you can turn off your Zoom and have your lunch, depending on which time zone you're in. So for the quantum Hall state, a little bit of, again, motivation why this might be an interesting way, let's say, to probe. Like forget about now many-body, we would eventually get to the many-body system, but just optical probe, why even in the linear regime would be interesting, is that the current approaches in the electronic transport measurement, they're in these two categories. They're either transport, so they are coherent but global, like Mach-Zehnder tunneling. We can get understanding of the global understanding, coherent understanding of how the electrons are going, let's say around the edge, etc. But we don't know about the locality of the system. SEM, SET, etc. They can give us local information, but generically they are not coherent. So we cannot understand the coherent phase properties of the electronic wave function. So can we use light, like in this cartoon picture, I have an extended state and I have some light either in a cavity or a free space, and then learn more about the properties of this. In most of this talk, I will focus on Dirac material in contrast to material with quadratic dispersion. So if I had quadratic dispersion, we can define this generalized momentum. And then for the uniform magnetic field, this generalized momentum would have a commutation relation of a harmonic oscillator. That's why we get this Landau level that are harmonically spaced. But if we start with the Hamiltonian, where the dispersion of the electrons is linear, then when I do the minimal coupling, similar to the minimal coupling that I did over here, then instead of getting this h bar omega c, this is Samson energy dagger A, I will get something like this, and I have to square this such that I get a harmonic ladder. So that's why if we have the strong magnetic field on graphene, then instead of getting these harmonic levels that are equidistant, like Landau levels of two-dimensional electron gas, we get the square root n dependence. So this is energy, this is the strength of magnetic field, and then you have this square root dependence, and these are the indices of the Landau. And why this is important for our talk is that they give us optical selectivity. So these non-equidistant Landau levels, they give us optical selectivity. In particular, there are some allowed transitions from several Landau levels. So for example, from Landau level -2 to 1, etc. And this has been observed experimentally by looking at transmission and absorption. One can resolve these light matter interaction. The reason I'm going back to this background is that we started to look at the light matter interaction in quantum Hall systems, and we already saw that in the non-linear regime, there are even surprises before going to fractional quantum Hall. So this is actually a very, has a big history, and gallium arsenide, and looking at the optical properties of it. And then more recently in Attach's group, looking at inside the cavity. Here I'm more focusing on graphene. Again, there is a question from Bill.
So I couldn't resist. I see at the bottom of this slide, there's a reference to Dickey superradiance.
Mm-hmm.
Could you enlighten us a bit?
Yes. So the people thought that, so this is, like, I can think of these Landau orbits as a spin. So I can go from one state over here to another state over here, but they're highly degenerate. So they can constitute a lot of spin, like in a spin ensemble. Then I can put a cavity resonant with that spin, and that would form a Dickey model. And if that light matter interaction is strong, then I should have this Dickey superradiance phase transition. We know, I think from the 70s, that Dickey superradiance phase transition cannot happen when the system has a quadratic dispersion. People thought that if we start with graphene, it's a linear dispersion. So if I do the minimal coupling and then do the Dickey superradiance, I might see this Dickey radiance super phase transition. But unfortunately, once you include the higher order corrections, the graphene is linear only around the Dirac point. When I consider all the higher perturbation orders, then it turns out that the Dickey superradiance phase transition cannot even happen in this system. So there were like a bunch of go proposals and no-go theorems, and then in the end, it turned out that there is no go. So you cannot actually see superradiance in the systems. So since you asked. So now let's look at these optical transitions. So as I said, there is some dipole strength that you can go from these lower levels to higher levels. So if you look at more carefully, you have the Landau level index. We go from Landau level n to n+1 generically, and go from Landau level orbit, Landau orbit m and m. These are in the presence of, in the absence of disorder, and in the symmetric gauge, the orbital angular momentum is a good quantum number, so we can index the Landau levels just using Rm. So just a simple exercise is that if I put now my Fermi level over here, all these states are occupied, and if I excite an electron over here, it will go over here, and then it comes back through a photoluminescence process and emits a light. So if I can do a spatial and spectral resolved photoluminescence on such systems, I can actually map out the disorder, because now in the presence of disorder, these won't be completely degenerate. They would have some, they would be affected by the disorder. But now if we resolve this photoluminescence, this is numerical simulation, one can reconstruct the disorder map. And this is kind of cool. Okay, so that's kind of not surprising. But what happens if we put the Fermi level inside the Landau level? In particular, if I have some edge state, if the system has some edge that bends these states, then some of these states will be available, some of them would be not available, so will be occupied. So when I do the photoluminescence, I can not only come down over here, but I can, in principle, go to other states. These transitions are usually very weak because they're beyond dipole approximation. Usually, we have in light matter interaction, we use dipole approximation. The electronic cloud is much smaller than wavelength of light. The dipole approximation is good. But what if my edge states and quantum Hall states are big compared to the wavelength of light? In this situations, one has to be more careful. So we have to look at this transition element. So we go from 0 Landau level and Landau orbit m to 1 and m prime. And in the middle, we have the vector field. So these are these wave function in the complex plane. So r radius, m is the power of this orbit, and then this is another orbit. And then for simplicity, we go to the cylindrical coordinate. So we just write our Maxwell's equation, and then these are the modes in the cylindrical coordinate. These are the Bessel functions. Now, immediately we see that m over here plus L should be equal to m prime, because the angular part of this integral should be non-zero. So that's our selection rule, meaning that if the electron changes in angular momentum, that difference of angular momentum should come from light. So that's okay. But usually, if that angular momentum is beyond 1, then the radial overlap of this integral is very, very small. And that's usually the case. So when you get the branching ratio as the strength of the orbital angular momentum, then it sharply goes down. But in the system, as I said, since my states can be very large, in the absence of disorder, they can be macroscopically large, then it turns out that we go beyond dipole approximation, and the light can be emitted with higher orbital angular momentum until the mode that it's so big that the whole of the Bessel function is bigger than the system size. So at that point, I can't emit. So that was kind of a surprising result. And then it made us actually think a little bit further that now if I can impart angular momentum to an electronic system, then can I do an equivalence of the Laughlin pump? Let's say in the Laughlin pump, you have the magnetic field that imparts angular momentum, and then you have a radial current. But in principle, one can do a Laughlin pipe with the light that has orbital angular momentum. So this is orbital angular momentum of light will be imparted of electron, and one should see these radial currents. So this is kind of our theoretical prediction, and then one can even apply these and go even crazier, and then use some of these pi pulses techniques or stirrup techniques in quantum optics to move the electrons one by one from the inner circle to the outer circle. So that was kind of the linear part of the story as a warm-up. And now I would like to not just use light as a way to probe and change the single particle behavior, but the many-body particle behavior. And that's the idea of this synthetic bilayer graphene. So we usually have a graphene that's one layer, and then we have another layer, and then there are very interesting physics in quantum Hall of bilayer graphene. What we thought through this collaboration was that if I have a single Landau level, if I have a single graphene, and then I drive two consecutive Landau levels, then I can think of the lower Landau level as one layer and the upper Landau level as another layer. So that would be like my synthetic dimension, if you like. And then the light that is coupling these two levels would act as the tunneling. So different Landau level plays the role of different layers, and light plays the role of the tunneling. Okay. So far, it makes sense. You know, it's the Hilbert space is the same size. So more specifically, you have the first Landau level, then you have the 0th Landau level, and there is some energy difference between them. You optically drive them. You optically go from one to this level, and then to this level. And then if you go to the rotating frame to get rid of this time-dependent part, then we have the energy offset, which would be a Zeeman field, like a perpendicular to the bilayer, and then the tunneling between these two layers. Okay. So far, I'm not doing anything. It's just the Hilbert space is the same. Yeah, there is a question.
Still about a single electron, and then using this idea of a synthetic layers to establish the geometry, and then maybe later we're going to get to multiple electrons, or are we already talking about electron correlations?
No, so far in my Hamiltonian, I have not put my Coulomb interaction. I will do it in the next slide.
Okay, so then I'm wondering, one of the things one often thinks about when you have bilayers is that there are interactions between the layers. That is, an electron in one bilayer sees an electron in the other bilayer, and they interact. If there's only one electron, then that's not happening, right? That's not part of the physics of the synthetic bilayers, at least at this point, right?
So, yeah, yes. So far, I'm just saying that the Hilbert space are the same. So if I have two layers and I only look at the lowest Landau level of two layers, the number of states available is similar to having a single layer and considering two Landau levels.
Okay, sounds good.
Okay.
There's also a question by
Anton had a question.
Yeah. Yes, right. Also speaking about the size of the Hilbert space, if I understand the transition frequency from the 0th Landau level to the first one, for example, in graphene, would also match another transition frequency from the 1st to the 4th, I forgot. So is there a way to isolate this as single transition so that you're dealing with bilayer and not facing a leakage problem?
With polarization.
Oh, okay, I see.
Yeah.
Yep.
And also changing the material, because there are also some other problems with graphene, and there is a whole industry and works on because these resonances that Anton mentioned are actually very important because they can also lead to Auger scattering and ruin a lot of things. And there are recent experiments in other material, I don't actually remember, it's in Nature Physics by Potemsky and company, that they looked at another material where you don't have that problem, and even the Auger scattering is not present. So Yangji has a question.
All right, thanks.
Yangji, go ahead.
Hi, Mohammad. My question is about the wavelength of the photon. Because here it seems that you assume it's a uniformly driven.
Mm-hmm, mm-hmm. So here, in contrast to the previous part that I really cared about the spatial, etc., here I don't care about the spatial part. Here it's let's assume that it's uniform. Good question. So now, let me go and look at the interaction, because that's when it becomes interesting. Because so far, it's very similar to the Fouquet topological insulator, that I have two bands and I drive it, and it may change the band structure, but not the interaction. What I'm claiming is that since I'm bringing these electrons and making them resonant with this one and not the other ones, assuming that there are no other states, as Anton mentioned, then these electrons can resonantly not only scatter through the lowest Landau level, but also scatter with the electrons in the first Landau level. So I not only have my linear interaction, but I have my Coulomb interaction, which is a mess, of course. We have different Landau levels, and then we have different Landau orbits. Because of this rotating wave approximation, let's assume that many of them are off resonant, and only like two levels are relevant. In particular, I can have like 4 processes that I will show in the next slide. So again, I just assume that I have only 2 levels, so that I have a pseudo spin. And now, since I assume we have rotational symmetry, I can cast this interaction using Haldane's pseudopotential. Okay, so similar to any quantum Hall system that I have rotational symmetry, I can decompose the strength of interaction as a function of the relative angular momenta of electrons. For a Coulomb interaction, for example, something like this. Here we would do the same thing. Okay, so now this picture, it might be actually easier to understand than the math on the left side. So in a real bilayer system, we have Coulomb interaction that can scatter my electrons in the lower state. So I can go from 2 orbitals to another 2 orbitals as long as I preserve the total angular momentum. I can also scatter electrons in the upper layer. And the same thing happens over here. So I can have interaction in the upper layer and interaction at the lower layer. Here we have the same thing, but since the Landau level 1 and 0 have different form factors, then the Z2 is broken over here, right? Because the Coulomb interaction is not the same in this level and this level. As Bill said, we have also electron between the layers. So this is this one. Again, an electron can go from here and an electron can go from here. And as long as the total angular momentum is conserved. And this is density interaction. But what we have over here is that since they all belong to the same material, to the same layer, we also have these cross terms that are not present previously. So I have to take into account all these four possibilities, and in particular that this is not present. And since my electronic wave function should be anti-symmetric, including the spin, I can rearrange these terms in the following way. So this is the Haldane pseudopotential of the system. So this is the strength of different Haldane pseudopotential. This is the relative angular momentum. When I couple, so this is the intra-layer, looking at individual levels, and this is the inter-layer, when I couple 0 and 1, and when I couple 1 and 2. So 1 and 2 is monotonically decreasing, very similar to a Coulomb potential. But what is interesting over here is that when I couple 1 and 2, then the V0, the Haldane pseudopotential corresponding to 0 orbital angular momentum, is smaller than V1 and V2. So now this kind of gives you a hint of what's going on, that by resonantly coupling one lambda level to another lambda level, I make some of the Coulomb interaction terms more relevant than the other ones. So this, what I call engineering the effective interaction. So I'm not changing the strength of Coulomb interaction, we're just making some of the terms more relevant and some less relevant. So it's not a hollow core potential, but it's, you know, it's a little bit closer than what you think with a normal Coulomb interaction. So what happens, for example, for a specific filling factor? So if I strongly drive these two levels in the regime that the drive is much larger than the Coulomb interaction, then I can think of these states that are hybridized. And if I can thermalize in this hybridized levels, in the lower state, then I have these orbitals, and similar way that we construct a Laughlin wave function by starting with just lambda orbitals and then making a Jastrow factor. Here, instead of starting with these Z's, I start with these hybridized orbitals that, let's say, it's half-half. So it was before lambda level 1 and 2, but now it's +1 and -1. And now I Jastrow factorize them and then make a lambda, make a Laughlin state. So this is exactly what we see. So this is energy as a function of omega. And if omega is very large, I'm talking about this regime, you see that the Laughlin state has a very nice overlap. And then as we decrease omega, things can change, but for this case, we didn't see any change. So if I couple 0 and 1, that dressed Laughlin state would actually remain a good description of the system. And if you look at the spin polarization in the sigma z direction, you see that the spin is polarized. So all the electrons are in one of these orbitals. Now, if I couple 0 to 1, then the Coulomb interaction can actually overwhelm this hybridization, and we can have a different phase. And in particular, in this coupling, it turns out to be the case. So over here, again, the Laughlin state is a good description of the system, as you can see with the overlap. But then when we decrease omega, then the system is completely unpolarized and becomes a spin singlet. So this was some indications that there were a bunch of scenarios that what kind of state this is the interlayer Pfaffian state, etc. So we collaborated with Abul Hassan Boezi and Zhao Liu, who have actually studied the system very, very thoroughly. And my student, Zipe, did the DMRG calculation to see how close we are to these Fibonacci phases that Zhao Liu and Abul Hassan and others have studied. And from the degeneracy of the Landau levels, from the level counting, from the entanglement entropy, we figured out that Fibonacci phase is the is the state. So that's all suggested towards the same conclusion. So if you're interested, we can talk about that. But I would like this colloquium to be kind of a survey of other things. So that was one idea, how can change, light can change the effective interaction, and we will see another example of it in the superconducting systems. Before going there, we had another work recently through this collaboration, using light to make a superlattice. So why it is interesting, because usually people have looked at the Fouquet topological insulator, a uniform field, and you get interesting physics, but now imagine that the light has some spatial structure to it. So in the high frequency limit, we will have some Hamiltonian like this. So you have the linear term, and then you have this optical potential that has a sigma zeta, and then it's spatially dependent. So this sigma z is important, because if it was just a unity over here, then you get Klein tunneling and the electrons wouldn't even see it. So why optical lattice in this structure would be even interesting? Because you will say that these electrons are in a lattice of angstrom. My light is like a micron or hundreds of nanometers. Why it would be interesting? Because this superlattice spacing is much bigger than the original lattice. But with the recent Moiré physics, we know that that's not bad at all. So you can have a superlattice that is at the length scale is much, much larger than the underlying lattice, yet there are interesting physics to explore. So in this work, we just looked at the simple square lattice and then a Kadome lattice. So you can, by light, imprint this kind of phases. So in the shallow lattice case, we have this Fouquet topological insulator in each region, but now since they are shouldering each other, these guys can talk to each other. If I go to a deep lattice, then I confine these currents, and then the electrons will orbit in these deep puddles. So not surprisingly, you see that if we are in a shallow lattice, then you can have a non-zero Chern number. But if in a deep lattice, these are kind of isolated orbitals that don't talk to each other. So then the Chern number is non-zero. And then since these guys are away from each other, the WKB tells us that the tunneling between them would be very, very weak. And you get flat band. You get power law decrease in the gap, and then you get flat band. This is not as flat as a Moiré lattice, so I don't want to oversell this. This is just the fact that these puddles are away from each other, and then you get basically exponential band flattening. So we can look at the other kind of lattices. We can look at the interaction now. Can we have like superconductivity in this kind of systems? If the superconductivity is not due to electron-electron interaction, if it's just phonon that has nothing to do with the strength of electron-electron interaction, then maybe just increasing the number of state using this exponential band flattening would be enough. So that's kind of one direction. The other, one important problem with all these proposals is actually the thermalization. So these are all driven systems. So yeah, there is a question.
Hello, can you hear me?
Yeah. Yes,
Yeah.
go ahead.
Yes, so my question is about the experimental realization of this type of lattices.
Yeah.
You need as many sites as lasers, or can you imprint this pattern with a single laser? Oh,
so okay. So that's a very good question. So this work was inspired by these recent works in cold atom. That they use a spatial light modulator and digital micro mirror devices that they can imprint any kind of superlattice structure that they want. So this was done in Anton Brouet's group and then also at Harvard. So there is a whole technology that has been developed by ultra cold atom physicists. So yeah, a single laser, but with some modulators in front.
Thank you.
Yang Ji has a question.
Hi, Mohammad. So can it be possible to have those regime with a different sign of mass? Because now it seems that you only have the same sign of the mass. If you have a different sign of mass, then there will be an intrinsic topological state, I think.
So you mean not only I change the amplitude of the mass, but also the sign of the mass?
Yes, they will guarantee you to have domain zero massless domain walls.
But that would be the last part.
Okay.
I kind of mentioned. So here we looked at graphene and high frequency domain. But if I now do the same trick in a semiconductor, then I have a resonant Floquet situation, then that is possible. So you can have light on this side and then invert the band, and then you can have no light on this side and you don't invert the band. So I think that's what you were thinking, right? So I can spatially change this, the sign of mass.
Yes, thank you.
Yeah. So, okay, so coming back to reality, because these are kind of interesting ideas, there are not many experiments, I have to say. Fortunately, there is this recent experiments in Andrea Cavalieri's group that it seems these topological insulators and the predictions are actually correct, but there are many unsolved questions regarding the thermalization. Like this pre-thermal, this steady state, or no, we have to think of it as a quench, that I start with some electronic distribution and then project the band into new band, and then they will be populated accordingly. So there is a recent work by Ludwig Matti and collaborators on how to understand this paper. So there's a kind of a very active field to understand this. But going more on the crazy part, one can think of maybe even do other types of interactions. So there was a work by Papik and company that they looked at three-body interaction engineering, but using like cold atom systems. Can one bring some of those ideas into the real material? And then can we construct, for example, twist effects or exotic topologies by light, making this kind of tunneling that these two folks proposed for material, but now using light to make these kind of structures, these staircases. Bill has a question. Yeah.
Yes. So I was intrigued by the heading thermalization in the driven system. Can phonons cool the system in the rotating frame? Now, the thing it immediately makes me think is that one of the problems with Floquet systems that are many body systems is that you don't come to a steady state. That is at least one of the dangers is that you just keep pumping energy into the system by means of this Floquet drive, which doesn't happen in a single particle system.
Correct.
So what I'm wondering is that already something that has been somehow solved in order to ask this question, or what?
So there are, I would call exotic bath solution. So exactly you said, I drive the system at long time, it's gonna heat the hell out of the system. But then I can engineer my bath in such a way that I can cool the system in that rotating frame. How realistic those baths could operate, that's again, one has to do experiments. There are a bunch of theories on that. So this experiment is pulsed. So this is not at the steady state limit. So some of these ideas are safe to consider in the pulse regime, but not steady state. Steady state needs, I think, way more work. So can I move on now? We are gonna switch gears. So that was on the topology, how we can do this kind of engineering effective interaction or superlattices using light. Now, superconductivity, can we use light or cavities or quantum optical techniques to do this. As an example, I start with this work as a collaboration with Victor Galitsky. So what happens when we irradiate a superconductor with electromagnetic field? Basically, you create your superconductor, you put it in the microwave. Is it going to survive, or you're going to break it? Contrary to the naive guess, microwave radiation actually enhances superconductivity, and it's known as Eliashberg effect. And experiments are kind of historical in the 70s and 80s, etc. So it's kind of a very established situation. A cartoon way of understanding is that you have this Cooper pair, and then you shine some light whose frequency is below the gap, such that it cannot break the Cooper pair. Instead, it can take these quasi-particles over here that are above the gap, and then take them somewhere else, okay? So as long as they go somewhere else and they don't come back, then effectively it cools the system. It reduces the number of quasi-particles in the system, and that's why superconductivity can be enhanced. So that's kind of one motivation. The other motivation are the recent experiments in Cavaleri's group, shining mid-infrared radiations to superconductivity and looking at high TC transient. So again, can we apply this cavity QED toolbox to this problem? So through this collaboration, Victor, John, Andrew, and Zach, we looked at this system. So we have superconductor, we put it in a cavity. So we have this, the idea can be understood very simply through this. I have this bougainville of quasi-particles that are usually thermalized with the bath temperature, like a phononic temperature. Now we couple them to some cavity photons. These are photons in the cavity. And then assuming that this cavity is cooled down to a temperature lower than the temperature of the phonon bath, then we can effectively cool down the system and enhance superconductivity. So if I look at the gap equation, if I get rid of the occupation of my quasi-particles, then I improve the gap. So that's basically the idea. So now, how can we do this? The interaction of light and matter is given by this Hamiltonian. This will be the cavity modes. These are thermally occupied, so there is no laser in contrast to the Eliashberg effect. It's just the cavity, empty cavity, but it's thermal, so it's thermally occupied. And then my electrons, and then I have to write the electrons, of course, in the Bogoliubov quasi-particle basis. We only keep the resonant terms and get rid of the non-resonant terms. And then the techniques is just Fermi-Goldman's rule. So it's a very kind of a simple situation. The processes are four. So one process is that I can relax, I can take a high energy Bogoliubov excitation and then come down. I can absorb a photon and then take a quasi-particle to the higher energy. So this is analog to the Eliashberg effect, that I shine some light, it gets absorbed and take a quasi-particle upstairs. I can also recombine these guys and then bring them down and make a Cooper pair, or I can excite a Cooper pair, break it, and then make quasi-particles. So the green process and the red process are good. The blue process and the purple process are bad, right? That's why it's complicated. So when you look at the enhancement of superconductivity gap, which is not very large, you know, it's like a fraction of a %, as a function of cavity resonance, which sets which of these processes are relevant, and that's the frequency with respect to the gap. Then you see the different behavior. So for example, for a cold cavity, which is the blue line, then the superconductivity will be enhanced for high cavity frequencies. For low cavity frequencies, it will be suppressed. And then for hot photons, then it would be not enhanced, but for low frequency cavity, it would be enhanced. So this is basically Eliashberg effect. that the frequency of my cavity is below the gap, and I have many photons in the system. So here they are not coherent, they are thermal, but they can lead to these red arrows and then enhance the superconductivity. So it's kind of basically a generalized and more universal picture of Eliashberg effect. Because in the Eliashberg effect, the coherence of the photons is not important. So instead of a coherent field, microwave field that I send, even if I send a thermal field or a squeeze light, etc., it does not matter. So this is a testament to that. Okay.
I have a question by Anton.
Yes. So I'm wondering if, so I imagine in a realistic cavity, there will be also higher harmonics that in the setting would couple to the condensate as well. Moreover, they would, I imagine, not be isolated in the frequency. So typically in a 3D cavity, the level of spacing is not extremely high. So do you know how this image would change if you include also the higher harmonics?
I don't have the figure, but in the paper we have the multi-mode situation. Yeah.
I see.
But you're exactly right. You're exactly right. And I have to say, still, even if that calculation in the paper, this is very cartoon physics. If one really wants to make a direct analogy to experiment, one has to be really careful to do a comparison with any experiments. There are many other factors that are important, like a polarization, etc.
Mohammad, can I ask a question?
Yeah, I'm sorry.
Yeah. It looks like there's a point where everything vanishes for different different temperatures and so on. What is there something special going on there between 2 and 3?
Not that I remember. Yeah.
Okay.
Yeah, you're saying that whether it's a universal thing, I don't remember. Yeah. So moving on, that was an empty cavity. As I said, there is also like ongoing experiment. There is even a recent experiment from Thomas Ebbeson's lab that it's not driven. So Andreas' experiments were all driven. These experiments are non-driven and controversial, and they have seen enhancement or actually destruction of superconductivity when they are close to some cavity. And actually, before that, we were kind of thinking about a similar line of thought. And this is this work by Hossein Dehqani, Zach Rines, and Victor Galitsky. And that's optical enhancement of superconductivity with a targeted description of charge density. So in many material, we know that there are these two competing order parameters. There is superconductivity and this charge density of bond density waves, and they compete with each other. So if we suppress one, it would enhance the other one. And many of the theory proposals and works to understand Cavaleri's experiment are based on that, how light can change these phonons, and these phonons destroy the charge density waves. So here we looked at an idea: can we directly just optically destroy these BDWs? And the idea is the following: we have this BDW phase, we excite them with some light, and they will go somewhere. Either they stay over there, or they come into the steady state and form a Cooper pair. So basically, by destroying them, maybe we can enhance superconductivity. So this BDW have their collective modes have some linear dispersion, and if our light wants to resonantly enhance them, then we have to satisfy the momentum and energy at the same time. The group velocity at the Fermi velocity. So with the normal light, you cannot do that because the speed of light is 3-4 orders of magnitude higher than that. So the idea was actually to use surface plasma polariton. That what it does is that you have some light, it comes in free space, but it shrinks the wavelength of light. Basically, it decreases the effective group velocity of light. And then we can do a momentum and energy matching, such that we have this light, we have the material with superconducting material, and we have some two-dimensional layer that provides this surface plasma polaritons, such that that energy momentum would be satisfied. So that's the work that Hossein did recently. So now, so that was enhancing superconductivity. We have a recent work by Pouyan Ghayami and Hossein. Then the question is that can we induce superconductivity by optical drive? So a usual Cooper pair, we have the following. We have some momentum and the opposite momentum, and then the spins in the opposite direction, and we pair them, okay? We pair them, and then we have a gap equation, and for that gap equation to give us some non-zero answer is that we have to have attractive interaction. So basically, that's the key point to have a non-trivial answer for the gap equation. Now, the idea that was worked out actually a long time ago by Galitsky, not the Galitsky of my collaborator, actually his grandfather, was that if we do the inversion of the population, then we might actually have superconductivity. And there are now recent works by Claudio Chamon and company kind of revived those ideas. And our work is built on that. So the idea is that now, if for some reason I can play with these populations such that I get a negative sign over here, then again I have a similar gap equation as my usual BCS. So how is it possible? Now we are not coupling electrons in a single band. We are coupling them in two different bands. And let's say one of them is the valence band, one of them is the conduction band, and they're in two different regions. One of them is in one valley, the other one is in the other valley. So I can selectively populate these guys and these guys, such that I can invert the sign of this 1 minus n minus n. So how is it possible? It's possible with a material that allows us to do that. And that's the work of Chamon and company, is that let's assume that I have a two-dimensional material like a HBN or TMD, that I have some optical selection rule, meaning that if I shine a sigma plus light, I can only excite electrons in one valley and not the other valley. Then the conduction and valence band population in two different valleys would be different from each other. Now, once we have that, of course, we have to solve the block equation, very similar to the exciton equation, to see how much excited states we have and how much holes we have in the valence band. And now we can look at the pairing across the valley. So we can have a pairing from the conduction band to the valence band over here, and conduction band to the valence band over here. Okay? Now, as I said, this is one valley, this is another valley, then these valleys would be populated asymmetrically. Why? Because they have this optical selection rule in many of the 2D material. And if I look at now this quantity of interest, at some point it can be positive or negative and have the right sign, basically. I'm not going to get into the details of that. Okay, so now with that in mind, if we now look at more carefully at the form of our interaction in the gap equation, since we have to project it into the into this block bands, and we have some Berry curvature, we should decompose it into different modes: 0, 1, SP, and D. And we get the following. So basically, by choosing the frequency of light, I can determine which momentum class I am exciting. So for example, if I choose a higher frequency for my drive, this dotted line will move up. If I choose a lower frequency, then these dotted lines will move down. I'm presenting this for the first time now. I realize I could have done a better job. So by choosing the frequency of my light, I can decide which momentum class I'm exciting and which momentum class would have the inverted sign, okay? The rest of them would not participate in the gap equation. Of course, we have to do the sum to make sure that we get non-trivial result. But that's the key. So if I look at this form factor and then look at the excitation frequency, then you see which one would win and which one would lose. These are the different channels. And now having that resonant condition in mind, one can actually look at the critical coupling and then see which one is favored. Depending on the frequency of the laser field, we can favor S wave or P wave. And as I said, this is a work recently done by Hossein Dehqani and Pouyan Qaimi. So with this, I would like to summarize. I presented some works by how we can use light to manipulate quantum Hall states or make interesting quantum Hall states. And the other one, how we can use these optical techniques to play with superconductors. So now there are some ongoing works and outlooks. One is that in the spirit of this strongly correlated system and then what happens to light-matter interaction, we've been recently looking at the Mott excitons, so similar to superconducting systems that you can have an exciton. Doubler and Holon in a Mott insulator can also form an exciton, and this is a recent work. We are currently looking at how we can use squeezed light to enhance superconductivity. That's a work in collaboration with Victor and our postdoc Andre. Creating multi-quantized vortices in flow K system. This is a collaboration with Ivar. This light, I said, can imprint orbital angular momentum. Can you actually twist these electrons in this flow K insulators further? And then other works with Attach and actually and Tobias that I did not really talk about. Here, I just looked at what happens to the matter. You can also look at what happens to light. So usually we shine light and we see what happens to the light when we integrate out the matter. And we usually assume that the matter is not interacting. But imagine that I have a fractional quantum Hall state, that it can be compressible, incompressible. That would have a huge significance in what the output light would look like. And there are a series of interesting experiments in Attach's lab. We wanted to make a comparison with that. There's some theory work. And some other ongoing works with Pouyan on optical manipulation of correlated states. So thank you very much for your attention.
Thank you. I'll give you a one person applause so we can hear it. So we have time for some more questions. I see Bill has a question. Please go ahead.
Yeah, so now returning to the last topic, the one where you were using this double valley approach, and it looked like rate equations that were being manipulated so as to enhance the superconductivity. It made me think very much of pumping a gas laser, and while I certainly realize that one has to be a little bit cautious in ascribing superconductivity to Bose condensation and ascribing lasing to Bose condensation, I'm wondering whether this is a fruitful way of looking at things, or am I just deceived by thinking that there's a connection?
Well, in the spirit that we would like to condense this, again, so first I start with my disclaimer that it was in the beginning of the talk about these two tunnels that are going in two different directions.
Yeah.
Just showing that we have pairing doesn't mean that we have really superconductivity.
Sure.
These guys should actually condense. And if we really want to show that this is a real superconductor, we have to show, let's say, Meissner effect, or look at the optical conductivity.
Yeah.
So yes, in a sense, if hopefully if all these things work, then they would condense and then form a superconductor. I think what you are referring to is that you want to make a distinction between a laser and a BEC.
Well, I don't know whether there should be a distinction, but it just looked like the cartoons you were drawing looked an awful lot like the kind of way you produce population inversions in lasers.
Mm-hmm. Yeah, I mean that's exactly it. So we use the same optical block equation, but instead of looking at what happens to light when I pump the system, I look at what happens to the electronic.
Exactly. Yeah. Yeah. So you're saying this is very much in the family of sort of classic laser equations, rate equations, and such.
With the difference is that in the classic laser equation, I have one equation for light that gets nonlinear gain, and I have one equation for the population, and sometimes I also have an equation for the polarization of the atoms. Here we have a fourth one or a third one, which is the pairing. So now we have to solve these equations all at the same time.
Right, right. Now, with respect to pairing, as you pointed out, just because you got pairing doesn't mean you're going to have superconductivity. But at the same time, in usual BCS theory, they do happen at the same time. So I'm wondering whether this is outside of that. I mean, certainly that's not what we expect in high TC, but.
So this goes back to the question of Fouquet topological insulator, that we are forming these pairs, but they are in this rotating frame. So would they thermalize in this rotating frame? And if they do, would they have some optical conductivity manifestation?
Okay.
So the good news about Fouquet topological insulator and this recent graphene experiment was that indeed it had some transport manifestation. So the electrons did their work, and then they had some actually manifestation in the transport. So I hope these ones would also do that. Otherwise, one has to think further and come up with a path engineering technique such that they would thermalize in the steady state. Or maybe it's just a transient physics, and that's already interesting. That you don't really need to thermalize. You quench, and then you see a transient superconductivity.
Okay, thanks.
Sure.
All right, there is also a question by Victoria. You're unmuted. Please go ahead.
Okay. I have a question. Could you please explain a bit what do you change in your system so that you obtain different symmetries, S, P, and D? It was very quick.
So I don't change. Well, they haven't. So what we are doing is that we're just decomposing the interaction into different channels. That's it.
The thing that gap equation, it has either plus or minus, and this will define your symmetry. For example, if you have not changing signs, and you will have S wave. If it's
in the gap equation, I have to sum over all my momentum classes, correct?
So you have different contributions, right?
Exactly.
So all of them are altogether existing, kind of, until you decide which one is dominating, right?
Exactly. And then what I was referring to, indeed, I went fast. So I have the interaction that comes over here. So there is a U as a function of K that comes over here. And there is these guys in front of it. And then these are usually not good. They're only good to have the right sign when I resonantly excite them. So this was this plot, that 1 minus NN becomes interesting for specific frequencies and momentum classes. So the optical frequency of the light would determine which momentum classes would give non-zero or the right sign over here.
Okay. Okay, thank you.
Yeah, sure.
So Mohammad, on this same work, next slide, why don't you have, well, even when you have this right sign and everything, you don't have an instability, it seems. You need a critical coupling. Or do you have an instability?
Yeah, this is the critical coupling. So the critical coupling would be lower over here and then over here.
Right, it's lower, but you still need a critical value of the coupling. It's not, you don't. So there is no way of having an instability even with all of the population inversion that we get.
I mean, we have a non-zero critical coupling, but that is the smallest, depending on the frequency that I choose. Then I would favor one versus the other. But what you're saying is that I would get even a non-zero, even a like a
so the usual VSF case with S wave, let's say, would have an instability when you have attraction, right?
Correct.
So I suppose maybe there is some kind of competition. You don't have sort of uniformly the same sign over all K space, or?
No. So okay. So here I have to sum over all momentum classes. That we agree, right? Because that's how I find my critical G, right? So this is an external parameter that I'm changing. This is not K. This is my omega outside. The reason I made all this discussion over here was that I wanted to see as an external parameter, as a function of the external parameter omega that I change, why some are favored versus the other. Correct? Now, so that's maybe I went through it a little bit quickly. So depending on the frequency, that's my knob that I fix. So it can be at any. That knob would determine which momentum classes have their population inverted. Okay, and then for the other ones, there's not inverted. Now I have to go and sum over all of that, and then find that the critical coupling for which one is lower.
Yeah.
And not surprisingly, it would have kind of the same region of crossing because the dominant players are determined by that external frequency.
Right.
I hope that's convincing.
Yeah.
If you want, we can chat.
Yeah, I'll talk to you more a little bit. I think I understood that part. I'm wondering why you don't ever get an instability as you change these populations with your external power. But okay, yeah, thanks. Right, I don't see any other hands raised. Okay, great. Well, let's thank Mohammad again for a great talk. And thank you. I've got to find I've suggested a couple times, maybe I should find the right audience clapping, you know, like the sitcoms.
Yeah, it's funny when you're giving a talk and you make a joke and nobody laughs.
Yeah. Yeah.